I welcome you all for this NPTEL online lecture on earthquake geotechnical engineering, and this is the last lecture, that is lecture number 60 on this course. What we are going to talk is some part of ground improvement techniques, which is verification and IS code. So, as we discuss the 6th module of this course, which is on ground improvement techniques, and all those listed here in the black color has been already over. In the last lecture today, we are going to talk in 2 chapters. One is verification of soil improvement, and once it is over, then we also going to talk about bit about IS 1893 part 1 2016, particularly what are the given things in that code related to soil. So, let us talk what are going to talk is the verification of soil improvement first, that is the chapter number 5 for this module. In this chapter, what topics to be covered, that is first verification of soil improvement, which can be done either using laboratory testing techniques, in-situ testing techniques, geophysical testing techniques, and then we are also going to have the other considerations, and the information for verification and other consideration has been taken from the book by Kramer, which is on geotechnical earthquake engineering, the reference, and this is gratefully acknowledged. Coming to the verification of soil improvement, all attempts done to improve the soil should be checked to confirm that the desired improvement has taken place or not. So, we have a number of techniques for soil improvement, but it is always not only desirable, it is must that once you improve the soil, then you need to again confirm whether the improvement which you have done is enough or not. Many times there could be improvement in the shear strength and other things, but that may be enough or may not be enough for the given requirement. So, it is must to check. The most direct way of verifying the effectiveness of a particular soil improvement technique is to measure the soil characteristic that was considered deficient both before and after improvement. So, there could be some soil characteristics which was weak. For example, you may require soil improvement for some specific purpose. For example, shear strength could be weak, or there could be more development of pore water pressure. So, what we need to do in this verification, you check on one side there is a condition where you have the soil, or let us say the strata, which is without ground improvement. Then again you improve the site and check again, if there is a sufficient difference, then you can say yes, soil has been improved. For example, if the improvement was undertaken to increase the strength of the soil, measurement of the strength before and after improvement would provide the most direct verification of the effectiveness of the improvement process. However, it is not always possible to measure the deficient characteristic directly. In such cases, verification usually accomplished using related characteristics that are more easily measured, but that is you can say indirect method. Verification may be based on the results of laboratory or field test. In many situations, laboratory tests have been commonly used for verification of soil improvement. Field testing techniques may be divided into in-situ testing techniques and geophysical testing techniques. So, for the verification, you could use what we call the field testing techniques, which could be in 2 categories: in-situ testing techniques, which is mostly geotechnical engineering, and another is geophysical. So, first of all, we have 2 categories, one is using laboratory test, another is field test. Coming to the laboratory testing techniques, laboratory testing techniques have a number of advantages over other methods for verification of soil improvement. So, they have a number of advantages compared to in-situ testing techniques, but at the same time they also have some certain drawbacks that can significantly limit their usefulness for certain types of soil improvement. The requirements of obtaining a sample, if you want to test in the laboratory, naturally first of all there will be requirement of sample need to be collected from the field, and the collection of the sample from the field, it could be advantage for many of the laboratory testing, or it could be even disadvantage also. So, it goes in the favor as well as in favor, which we are going to discuss later. Obtaining a sample of improved soil allows visual inspection of the effects of improvement. So, first of all the good point that if you collect the sample of the improved soil, so what do? You collect a sample from the site which is not improved and another which is improved, and the test in the laboratory. So, while you can have the visual inspection, the good point, like once you collect the sample, you can there find their index properties, you can have visual inspection also and then test and then compare. But disadvantage is there that this how good this sample is representing your the field condition, how it is representative. It is okay when you have undisturbed sample particularly for cohesive soils, but for cohesionless or sandy soils it is difficult to get the undisturbed sample. Laboratory test allows greater control and more accurate measurement of stress, strain and environmental conditions than that are possible in field tests. So, this is the advantage, that means you can control many of the parameters which you cannot control in the field. That means a parametric study can also be conducted in the laboratory, but that is in the field whatever condition is there you need to test in the accordingly. In some cases this flexibility may allow more accurate characterization of the properties of the improved soil. On the other hand, laboratory tests only provide verification of discrete points, because in the laboratory test what you do collect? You collect a small sample which is tested in the laboratory. Now, there is a problem that how this small sample which you are testing in the laboratory represent the actual condition on the ground. So, when soil improvement is used to improve or eliminate localized zones or seams of weakness, verification by methods that require discrete sampling may be ineffective. Laboratory tests may also be influenced by the inevitable effects of sample disturbance, a problem that is particularly significant in the improvement of liquefiable soils. So, the density changes produced by even thin walled samples can lead to considerable uncertainty in the evaluation of improvement effectiveness. So, what you want to judge in the lab whether the conditions which you have in the field is effective or not. In that case, first thing is that the sample which you are testing in the laboratory, how good it is representing the field conditions. So, that is also the issue. So, many of the disadvantages of the in the laboratory test goes in the favor of field test, or we call in situ testing technique. So, here verification effectiveness may be overcome by the use of in situ test. Therefore, the use of in situ test for verification of soil improvement effectiveness has increased dramatically in the past 7 decades. So, in the like many decades now, the in situ test or field tests are preferred than the laboratory test, because they are direct tests. Because many geotechnical seismic hazards are evaluated using in situ test parameters, those parameters can provide direct evidence of hazard mitigation. And in in situ test, what are the different tests? Most popular is SPT, that is standard penetration test. Then you have cone penetration test, CPT. Pressure meter test, that is called PMT in the short, can also be used for verifying soil improvement and effectiveness. The SPT and CPT tests are performed relatively quickly and inexpensively compared to sampling and laboratory testing. The CPT is useful because it provides a continuous record with a depth. The PMT is more expensive, but it also allows measurement of lateral stresses and direct measurement of strength. So, like compared to SPT and CPT, PMT is expensive, but it is providing the measurement of lateral stresses in better way. Interpretation of soil improvement effectiveness from in situ test results must be performed carefully. The penetration resistance of granular soil, for example, is influenced not only by density and overburden stress, but also by lateral stress. So, in fact, you may know that in SPT the corrections are applied for what we call the overburden pressure, and then also correction is also applied for dilatation, dilatancy, which is when for the particular for saturated sand, when the fines and silts are there in the, and when the N values is greater than 15. Soil improvement techniques that result in increased lateral stress may produce unconservative estimates of the density of the improved soil if the post improvement stress state is not carefully considered in the interpretation of penetration test results. So, we need to consider the stress conditions also while interpreting these results. Because time dependent changes in strength, stiffness and penetration resistance are often observed after densification. That means with the time, actually today you may have different condition in the field, after few days it could be different conditions. So, therefore, in situ test performed immediately after densification may not reflect the actual degree of improvement of the soil. Yeah, so here verification testing is usually performed at least 72 hours after densification is done, because you have done some let us say densification at the site. Now, this densification to be effective, some minimum time is required, and it is suggested at least wait for 72 hours, because after like time passes the densification might be effective. So, as a result, first of all minimum times recommended is 72 hours, that is 3 days, and another thing that this could be, the densification should be with respect to time, how long it has passed since the improvement has been done. So, many of the soil improvement techniques are applied at a grid of treatment points, and the degree of improvement usually decreases with the distance from the treatment plant. Yeah, this is particular for densification. When you do the densification, you do in the grid pattern, you applied load here, densified and another point. So, naturally the densification will be more effective near where you are doing the treatment. So, as you go away from the point of the treatment, then this effectiveness will decrease. The relationship between the location of the in situ test and the location of treatment points should be considered in the interpretation of soil improvement effectiveness from the in situ test. So, particularly these tests will be have limited effectiveness if you want to verify the grouting effectiveness. So, the 2 points to check, one is the time which is elapsed after the improvement, and the second thing is the distance, that is location of your testing site with respect to the point where the improvement has been done, need to be considered while we we use the in situ testing technique. Now, another category, that is the third category, we discuss about laboratory test, then in situ test, and the third one is called geophysical testing techniques, where geophysical equipment like methods are used. And what is geophysical methods? We already discussed when we discussed dynamic soil properties in very much detail. Many soil improvement techniques increases the stiffness of the treated soil. The effectiveness of these techniques can be verified using seismic geophysical techniques. In most cases, it is desirable to perform seismic tests both before and after improvement. So, the same test need to be performed. What was the condition before the improvement and what was the condition after the improvement? For example, some of the test which is used is called cross-hole and downhole, and when we talk about this cross-hole and downhole test, including seismic cones, we already discussed in detail about these tests when we discuss the the dynamic soil properties. They are most commonly used for verification of soil improvement. Using these P or S wave velocities, which is like that you have seismic reflection test, seismic refraction test also come in this category, then you have SSW or MSW test. Thereby, so using the P or S wave velocity, which is body waves, can be measured over considerable distance, thereby providing stiffness measurement. However, each require at least one borehole. When you use the cross borehole, at least one borehole will be required in uphole and downhole. In cross borehole, minimum 2 boreholes are required, which we was also discussed earlier. For sites where soil improvement has been performed over a large area, seismic reflection and seismic refraction test may be useful for verification purpose. So, if you want to have on the large area, then 2 tests which we have discussed, seismic reflection and seismic refraction, both tests has been discussed when we talk about dynamic soil properties, and they could be useful for verification purpose. Then there could be SSW, spectral analysis of surface waves, and the most popular version of SSW is called MSW, that is multi-channel analysis of surface waves. This provides similar information without the need for the boreholes. So, the good point with the geophysical techniques are there that you do not require the borehole except in the cross borehole test. So, for cross hole you require the borehole, but for seismic reflection or SSW test, borehole is not required. At sites where stiffness changes irregularly in 2 or 3 dimensions, the result of may be very difficult to interpret. Such tests may also be performed when background noise will not adversely affect their results. So, while conducting SSW test, if it is isotropic condition, fine, but if your strength are varying not only in one direction, let us say along x direction, along y direction, of course it varies along the depth. In that case, it is difficult to interpret their results. Now, this was about verification of ground improvement techniques. There are other considerations also which need to be discussed. So, what is in the other consideration? The application of soil improvement techniques to the mitigation of seismic hazard, particularly against liquefaction, is increasing. So, that is that the technique which you use, and that techniques are used for mitigation of these hazards. For example, the threshold underpinning of many soil improvement techniques are poorly developed, and empirical observation of the performance of improved soil in actual earthquakes are rare. Because of these factors, it is particularly important to review the relevant geotechnical engineering literature before attempting to mitigate seismic hazard by soil improvement. So, using the soil improvement, your objective is to mitigate the seismic hazard, but what type of seismic hazard you want to mitigate, then relevant the literature should be quoted. For example, one of the seismic hazard which is use for we do for seismic hazard is liquefaction, and your objective when you improve the soil, your objective is not only simply increase the shear strength, but one of the objective in many cases is to mitigate liquefaction, or you can say to increase the liquefaction resistance of the soil. The effectiveness of many soil improvement techniques can be difficult to predict in advance for a particular site. Furthermore, the equipment, procedure, experience and skill of the soil improvement contractor can strongly influence the soil improvement effectiveness. So, here this is the issue. First of all, sometimes it is difficult to predict in advance before you do actual soil improvement. The second thing, and it depends like also what type of equipments are used, what type of procedure, what type of experience and skill development. For these reasons, it is frequently beneficial to construct test sections before beginning production work as or even before final selection of a soil improvement technique. Track sections allows site and protective specific evaluation of soil improvement at a moderate cost. Their use is advisable whenever possible. So, now coming to here, like this was what we have discussed in the first part of the chapter number 5. We talked about verification of the soil improvement techniques and other considerations. Now, the last chapter of this module 6, that is chapter 6 on IS 1893 part 1 2016, and this is the last topic which I am going to discuss related to this code. And the reference for this is code which is titled as Criteria for Earthquake Resistant Design of Structures, that is part 1, General Provisions and Buildings, and published by Bureau of Indian Standards, New Delhi. And this is, many of you already may be aware, that is this map, what this map is saying? This map is nothing but seismic zonation. This shows seismic zonation for our country and published in 2016. For the purpose of determining design seismic force, the country is classified into 4 seismic zones, and these zones are different colors, like orange color is zone 5. So, you could see the whole of the northeast area, all the 7 states come under zone 5. Then Andaman Nicobar Islands are in zone 5. Then you have different pockets in the country, and there are 5 pockets. One is in Bihar, which is near Darbhanga. Then you have in Almora and the Pithoragarh region in case of Uttarakhand, that is the eastern, which is the parts of the Uttarakhand state which share the border with the Nepal. Then if you go in the in case of Himachal Pradesh, Mandi, for example, IIT Mandi is in seismic zone 5. Then the capital of J&K, which is Srinagar, is also in zone 5. Then the Kutch region of where the Bhuj is located, where Bhuj earthquake occurred, is also in zone 5. So, 1, 2, 3, 4, 5 pockets beside the northeast comes in seismic zone 5, and whole of the Himalayan region, that is including starting from Ladakh, J&K, Himachal Pradesh, parts of the Punjab, then Himachal Pradesh, then you have Uttar Pradesh, parts of the Uttar Pradesh, and then Sikkim, Bihar. So, all this Himalayan belt falls in seismic zone 4. So, whole of the Himalayan region either it falls in seismic zone 5 or seismic zone 4. So, whenever you and that is why a lot of earthquakes, and the simple reason is that many of the earthquakes are originating in the Himalayan region. so which is seismically very active. Our capital of country, that is New Delhi, falls in seismic zone 4, capital of Uttarakhand Dehradun, capital of your Himachal Pradesh Shimla, then Chandigarh, they all falls in seismic zone 4. And then Gujarat is interestingly one of the state where all 4 zones of seismics 4, 5, 4, 3rd and 2nd zones are there. So, this was about seismic zonation of our country. If you see in general, the Himalayan belt in seismic zone 4 and 5, but if you go in peninsular India in southern part of the country, you find mostly zone 2nd and 3rd only. Only small pockets, for example, here near Goa, zone 4 or in Gujarat. So, otherwise in zone 2nd and 3rd only. So, all of the country's southern parts in either in 2nd or 3rd. When you design the structures of using this code, there is called design seismic coefficient, and this design seismic coefficient is calculated based on design horizontal seismic coefficient AH, and this seismic coefficient AH is dimensionless. So, this design horizontal seismic coefficient for a design of a structure is given by this relation Z by 2 SA by G R by I. What is Z here? Z is called the seismic zone factor, I is called importance factor, and this will depends on your structure, and it may be specified in the given, there are 5 parts of this code. So, different parts of the code 1, 1st, 2nd, 3rd, 4, 5, it may be specified what should be the value of I should be taken. If it is not given, then I should be taken 1.5 for critical and lifeline structures. For example, you have the bridges or hospitals or dams, the value of I should be taken 1.5, 1.2 for business community structures, for example industrial areas, then 1 for the rest of the structures, for example residential building. So, the value of I importance factor varies from 1 to 1.5, minimum is 1, maximum is 1.5. Zone Z will be taken as a zone factor from the given zone, which we will discuss separately for different zones, and R is called response reduction factor. So, the zone factor is given here, seismic zone factor Z in this slide. So, for zone 2nd, for zone highest zone 5, the zone factor Z is taken 0.36, while for the lowest zone it is 0.1, and for others 0.24 and 0.16. For in fact, these are the values. So, like the data like 4 zones are there, and for each zone what is the value of zone factor, it should be remembered by heart. And we in the design philosophy we use 2 types of philosophy. One is called equivalent static method and another is called dynamic analysis method, and we will discuss for both the methods what is the value of SA by G taken. So, we already discussed Z, we discussed importance factor. What is R here? R is called response reduction factor, which is also given in the different parts of the code 1 to 5 for the corresponding structure. And this R response reduction factor will basically indicating the ductility, and if you have the reinforced condition, then the value of R is expected to be taken more. Then finally, what is SA by G in this equation? SA by G in this equation is called design acceleration coefficient for different soil types normalized with P ground acceleration corresponding to natural period T of the structure, that is considering SSI if required. So, depending on the SA by G values, it depends on 2 factors. One is period, natural period T, and the second is type of soil for different soil types, and it shall be given as given in a parts 1 to 5 for IS 1893 for the corresponding structures. When not specified, it shall be taken as that cell corresponding to 5% damping given by expressions as follows. So, before expression let us discuss that this is the that for equivalent static method, the value of SA by G, variation of SA by G with natural period T is shown in this figure. And here what you could see, when the natural period is increasing from 0 to 6 seconds, the SA by G is also like here. So, up to certain value of period t, which is in any case less than 1 or even quite less than 1. So, it remains 2.5, and these 3 curves are for 3 different types of soil. Type first is for rock or hard soil, second is medium soil, and third is soft soil. So, if you have the weak soil for the given natural period, for example 1 second, you will have the highest value of SA by G and lowest value will be for type first. So, this curve is the for type first, this is for type third soil, and this is naturally for type second. So, the value of SA by G remain constant up to certain value of T depending on your soil types, that value is also constant 2.5. And further, so this curve can be divided into 3 parts. Let us say for if I discuss this curve for third case type of soil, this is the first part. The second part, in all the curves become constant value after 4 seconds. So, in this case 3 parts are there curve and this is listed here. So, for up to 2.5 second the value for SA by G is 2.5 up to 0.4 seconds. So, this is for type for rocky site, let us say for soft soil it is going up to 0.42. So, this is correspond to 0.42, this is up to 0.67 second. So, here this value I can put it the numbers here on the curve, it is like up to 0.4, 0.55, 0.67. So, this is 0.44, this is 0.40 and then 0.55, this value correspond to 0.55 and here this number is related to 0.67 second. So, in this case up to 0.4 seconds this is 2.5, here up to 0.55 and 0.67 second. So, this value is shown here and the value is also constant 2.5. Then if your value is between the time period is 0.4 to 4 second, then you can find using 1 by T, the reverse way. If it is more than 4 seconds, then it is become constant and the constant value you get is 0.25. This is similarly for medium soft soil sites and the third is for soft soil sites. For the given period except for less than 0.4 second, if this is the, if I draw less than 0.4 second is this value, this is less than 0.4 second. So, less than 0.4 second irrespective of your type of soil, the value of SA by G is constant, which is 2.5, okay. And then after this it depends on your type of soil. If you are weak soil you will get higher value of SA by G, for the rock or hard soil you will get the less value. So, this was equivalent static method. Another method which is called response spectrum method, the curve for SA by G and T is quite similar except that you get like instead of 2.5 flat, there is between this varies between this one. So, now what is this axis, if I draw, what is the value of this time period, and this time period is given here, this is 0.1 second. So, up to 0.1 second it is different 0 to 0.1 second, rest of the things are same as we discussed in the response. So, up to 0.1 second for rocky or hard site it is 1 plus, for all 3 sites 1 plus 15t, 1 plus 15t. So, this remain constant, the first row is constant. So, now your response spectrum has been divided into 4 parts, one part, the second part is here, third part is goes here. So, second and third part, third fourth part is similar as we discussed 0.1 in the last case also. Now, there could be a question that how we define this code, what is rock or hard soil, what is medium soil and soft soil, that is also given in the code itself. Therefore, determine the correct spectrum to be used in the estimate of the types of soil on which the structure is placed shall be identified by classification given in the table. And the soil types, first type is rock or hard soil, second type is called medium or stiff soils, and third type is called soft soils, and these are defined like here. Type first, simply if you have SPT n values are available, for type first the value of n should be 30. So, for first type of soil the value of n should be equal to 30, while for type second soil the value of n should be between 10 to 30. If it is falls between 10 to 30, then you say the type second. Similarly, for type third the value of n should be less than this is 10. So, if n is less than 10, then you say that is this the medium like the weak soil or soft soil. So, how this is defined? The values of n which need to be used using this table shall be the weighted average of the n of soil layers from the existing ground level to 30 meter below the existing ground level. So, you calculate the values from top to the up to 30 meter, but if refusal comes, then you need to count that layers only. Here the n values of the individual layers shall be the corrected values, and these should be corrected values, that means those values which are already corrected for overburden pressure. So, in this case now we have discussed all the things in the design horizontal seismic coefficient. Z has been discussed, SA by G has been discussed, R and I has been discussed, all the things has been discussed, and that this value of AH can be calculated for calculating the seismic weights. One of the important issue which is given in the code also in a table, that has been the minimum value of n which is required. If the desired value of n is less than these values listed in this table, then ground improvement is must, and particularly for liquid. And this has been divided into two categories. Seismic zone 3rd, 4th and 5th has been clubbed in one category, while zone 2nd is another category. For 3rd, 4th, 5th seismic zone, it says the n minimum n value up to a depth of 5 meters should be 15. If your depth is more than 10 meter, then minimum n value is 25. However, between 5 and 10 meter, the values of n, which is the minimum n value required, it can be found out from the interpretation. For example, for a depth of like you have the depth z equal to 7.5 meter. So, 7.5 meter, the n minimum n required will be 20. So, it will be between 15 and 20. So, this was for zone 2nd, 3rd and 4th. While on zone 3rd, 4th and 5th, zone 3rd, 4th and 5th, for zone 2nd, these values could be up to 10 and 20. So, that means in any zone, any seismic zone, the code suggests the minimum n value should be 10, not less than 10. If it is less than 10, then ground improvement technique is required to be must. If soils of lower n values are encountered, then those specified in the table shown above, then suitable ground improvement technique shall be adopted or default should be used. And these values are particularly must minimum value to avoid liquefaction. If your soil conditions are liquefiable and n values are low, then if n values are less than the values which is given in this table, then that means the soil is going to be liquefied. So, this was about for the minimum values required for ground improvement technique. Now, this code also have a one map which is approximate, not very accurate, like in the this shows map in general showing principal lithological groups in our country. So, you could see the yellow in this region is alluvium soils, which is Gangetic belt, and this one, and this is liquefiable soils. Then if you go in the particularly in the southern part of the country, then you have crystalline metallic rocks are there. Then in the Maharashtra region you have volcanic rocks and minor. So, basically yellow, then you have the this green and then red colors, and blue also sedimentary rocks are there. So, one and then laterites with the black color. So, you have which is a small portion 1, 2, 3, 4, 5 and the 6 is data not available, which is most the sum of the sites including Himachal. And so, this was what has been given regarding the soil or ground improvement techniques or for the geotechnical earthquake engineering point of view in the code IS 1893. So, with this I conclude this course, and thank you very much for your kind attention. Thank you very much for patience hearing, and as I already acknowledged during my promo this lecture also, as well as during initially, that many of the material in this course has been taken for this from the Kramer's book. So, that is gratefully acknowledged, but this has been will not be used for any commercial purpose. It is just for this educating the masses, and it is with the full credit is given to the Kramer's SL Kramer. Thank you very much for your kind attention. Thanks.